Sounds good. Thank you very much. Hopefully the presentation would be slightly shorter than that. So I'm, as Dimitri mentioned, I'm Jahandad Khan. I'm a staff software developer at AMD, and I'm primarily working on MIOpen, which is AMD's offering for machine learning on AMD GPUs. Thank you very much for the opportunity to speak here and share some of our work with everybody else. In recent years, machine learning has come to the forefront, and we have GPUs to thank for much of that success, primarily because of the immense computational power that GPUs afford, which is really useful for training large and deep models. However, another important piece of the puzzle is open source software. I mean, fantastic libraries like Pandas and TensorFlow and PyTorch, all of them have enabled some really interesting work, which allows other researchers. Yeah, so open source is certainly a huge piece of that puzzle, and we owe it to much of open source software for quite a lot of the development that has happened in the machine learning arena. So open source software such as TensorFlow and PyTorch, they rely on low-level libraries for convolution and BLAS operations, because convolutions and BLAS operations are, they require to have an efficient implementation of these computer-intensive operations. You require a very intricate knowledge of the underlying hardware, and that even if you had that, it requires a lot of time. So having open source implementations of these operations, it is really nice for other people, so that they can actually exploit that to use it for their own benefit. So what these higher level frameworks do is that they convert any model that a user might write in Python into a computational graph, and then they map that computational graph onto lower level primitives and then different devices. So this is where, so for an AMD GPU stack, what you would be relying on is called the Radeon Open Compute, or in short, the ROCm Stack. The ROCm Stack is AMD's open source offering for machine learning computation and computation in general. So whether you are in the HPC domain or whether you are doing machine learning, you can exploit the ROCm Stack to perform your computational operations and on an AMD-based GPU. So this includes the entire driver library, the runtime library, and the compiler. And this allows you to use an AMD GPU on a Linux-based machine to exploit all the computational capacity that GPU offers. So, to exploit this, what the ROCm Stack consists of is, as you can see, it is based on the Linux operating system. You have the ROCm driver, the ROCm system API, and the language runtime. So whatever code that is for the device or for the CPU, it is compiled using the compiler and the GPU-based compiler into a holistic code object. That code object is then transferred over to the language runtime, which converts, which consumes it and then launches the kernel on the host or the device as the programmer has intended. MIOpen builds on top of ROCm different machine learning primitives such as convolutions, activations, etc., to allow frameworks and other users to exploit them and accelerate their models. The good thing about MIOpen is that it is completely open source and is developed in public. It supports various machine learning operations such as convolutions, batch normalization, pooling, dropout, etc., as well as it supports HIP and OpenCL runtime. So most of the traditional machine learning frameworks use the HIP runtime, whereas some other machine learning and vision-based systems use OpenCL, such as OpenVX, whom you've heard from a little while ago. So whether your application is in HIP or OpenCL, in either case, you can easily use MIOpen to accelerate your machine learning application. The key part about MIOpen is that it is a single GPU library. So MIOpen only sees a single GPU. So that does not mean that if you have multiple GPUs, you cannot do multiple GPU-based training. What you can do is So the way it works is that if you have a ROCm-enabled TensorFlow implementation, then the TensorFlow implementation would actually deal with the multiple GPUs. So you can use ROCm with multiple GPUs, but MIOpen does not afford that functionality. So on a very high level, MIOpen is essentially a kernel store. So it's like a database which has a bunch of kernels, and then you ask it to you ask it to do a certain operation, and then based on the attributes of those operations, MIOpen would choose a kernel for you and launch it. So let's say you want to do convolution, you use the convolution API to tell MIOpen that A, you want to do convolution operation, and then B, what type of convolution or what parameters does that convolution have? What is the filter size? What is the stride? What is the dilation? Typically, the features that you would specify in a convolution layer, either in Keras when you're using PyTorch, whether you're using TensorFlow or PyTorch, that's the typical parameters you specify when you create that layer. MIOpen looks at those parameters, decides what is the best kernel for that operation, and then compiles it if it is not compiled already, or if it is already compiled, loads the compiled code object, then launches that kernel for you. So if you are a framework, what you see is that you specify the stream handle that represents the GPU, and you specify the GPU memory for that particular operation. So these two bits are supplied by the framework, and then the framework interacts with MIOpen using the C API. So this way, the C API essentially abstracts all the lower level details and all the intricacies of selecting and launching a kernel, whereas the framework only has to deal with memory and to specify what GPU it needs to run on. So an important part of this is that the framework is that MIOpen does not allocate or deal with GPU memory at all. That is completely up to the framework how it wants to allocate, how it wants to manage. So this allows the framework to completely to do interesting memory optimizations, such as common buffer elimination and stuff like that, which allows greater efficiency, etc., on a model-based level. Whereas it also frees MIOpen from the burden of doing memory management on the GPU, so it's sort of a win-win. So delving a bit more into the detail for about the kernel selection, etc., what you don't want in general is to have MIOpen compile the kernel again and again, because compiling a kernel is generally a very tedious and expensive operation in terms of performance. So to enable that, MIOpen has a cache hierarchy inside which ensures that if a kernel is compiled once, it does not have to be compiled again and again, and therefore can be served to the user over and over again. Because, for example, if you're running ResNet and you want to train it, the first time a kernel is compiled and it is run, you want to reuse the same code object again and again. So to enable that, what MIOpen does is that when an API call comes in, it chooses a kernel, and then it looks inside its kernel cache whether that particular kernel has previously been compiled. And if it has been previously compiled, it loads the code object and then serves it. On the other hand, if there is a cache miss, then MIOpen would compile that kernel, update its kernel cache, as well as serve the kernel to the user. This means that if the user has already compiled that kernel, whether in this invocation of MIOpen or a previous invocation of MIOpen, it does not need to recompile the kernel over and over again, and can realize a significant performance gains, especially in startup time. However, if you're running generally a known network such as one of the variants of ResNet or ResNext or other popular models, then you might want to avoid the first iteration. And to enable that, what you might exploit is something called a precompiled kernels package. So if you have this cache already, if you have this cache already installed using a third party, then you would, even on the first time, you would not need to load it. So To enable that, MIOpen supplies a precompiled kernel package called MIOpen kernels. So this is specific to your GPU architecture and the number of CUs you have. So if you have, say, a Radeon 7 or a Vega GPU, you can download the MIOpen kernels package for it, install it, and that would allow MIOpen to even skip the initial compilation time and directly load that, that code object from this installed package. MIOpen also supplies a script that can automate the download and installation of this package in the utils directory. So if you don't know what your GPU is, or if you don't, or if you just want to automate that process, you can easily use that script to download and install the package and then run it. As far as kernel development is concerned, MIOpen uses both HIP and OpenCL kernels. So some of the MIOpen kernels are written in HIP. Some of MIOpen kernels are written in OpenCL, and even some are written in GCN ISA. Okay, I think they have the URL, and so it's likely they're probably doing it. Okay, so a bit more about MIOpen development. MIOpen is completely developed in the open, so you can look at all our development process and all the future plans, etc., on our repo. If you find a bug or if you have something to contribute, you can easily open a pull request. More importantly, if you face any issues or bugs, you can always open an issue on our GitHub repository, and me, along with the rest of our development team, we would be we usually are very quick in responding to those issues, and hopefully you'd get feedback about whatever issue you're facing and way forward. So now I'd delve a little more deeper into the different MIOpen operations. So first and foremost is convolution. Convolution is a very important operation in the vision-based networks. It is also important because one, it affords a lot of information about the image, but it also is very compute intensive. So you need really high quality compute kernels to actually achieve it efficiently on a GPU. And this is also further complicated by the fact that there's many types of there's many types of convolutions. So transpose convolutions, depth-wise convolutions, group convolutions, and amongst each of those types, there's dilations, striding, etc. So all these parameters make it very complicated to come up with one universal implementation that can serve all of these convolutions. And not only that, in recent years, we have 2D and 3D convolutions. So needless to say that MIOpen supports all these types of convolutions, but it also has multiple implementations and multiple kernels amongst those implementations that can serve these convolutions. And we'll see in a bit why that might be important. So there are a few popular networks that are supported inside MIOpen for solving convolution problems. So the fastest among them is Vinograd. However, it suffers from lower numerical accuracy. And Vinograd is, for those who don't know, is based on the FFT algorithm. The direct algorithm is essentially the direct implementation of the convolution operation inside a kernel. The advantage of this is that it does not usually require workspace. Another algorithm that we have is called implicit gem. Implicit gem does not on the fly converts the convolution problem into gem inside the GPU memory, and then performs a matrix-matrix multiplication on tiled matrices to carry out the convolution. And the fourth supported algorithm is gem itself. So that means that the convolution problem is actually explicitly converted into a matrix multiplication problem in the GPU memory, in the GPU device memory. So the weight matrix is unrolled into a circulant matrix, and then the image and the circulant matrix are multiplied to carry out the convolution itself. For those of you who might be interested in, say, very high precision convolutions, they can go ahead and disable Vinograd algorithm if that is causing issues in their models. And along with these, there are many other environment variables that MIOpen supports if you want to tweak the behavior of MIOpen in any way. So as I was saying earlier, so for any convolution, there might be multiple choices to actually do that. So you might have algorithm 1 and algorithm 2, 3 algorithms that can support, and among those algorithms, there might be multiple kernels inside MIOpen that can choose the best, that can carry out a certain type of convolution. So the question is, how do you choose between them? So what MIOpen currently does is that it benchmarks the different kernels and the various algorithms inside MIOpen, and then serializes the result onto something that we call the find database. And then when you do it the next time, it actually reads the cached find database and uses the same result to perform the convolution. The variety of algorithms and the kernels is not the only thing that makes a convolution complicated. For each kernel, as a high-performance kernel, it might have further parameters such as tile size, the vector load width, et cetera, et cetera. And this might complicate matters for a particular convolution kernel because these parameters need to be known at compile time. So for the most popular networks, MIOpen already ships with, excuse me, MIOpen already ships with such tuning parameters for these convolution kernels. However, if you are a developer working on a model that has some new convolutions or some new types of convolution parameters, then you might it might be useful for you to tune these kernels for best performance for your model. So the way it would work is first you write out your model with the various convolution types, with the various convolution parameters such as filter widths, etc. And once you have zeroed in on the specific stride and dilation and filter height width, image height width, etc., then you can set a special environment variable inside MIOpen that would allow you to tune those convolutions. And once you have tuned them, you can use that tuning result for running training procedures after that, and hopefully it would be much faster than it initially was. Another important operation that is supported by MIOpen is RNNs. So RNNs are very useful for sequence models, sequence-based models used in image captioning, language models, etc. And much like everything else in machine learning, RNNs also have quite a bit of variation in them. They have, there's the plain RNN type, also known as vanilla RNNs, and then there's LSTM-based RNNs and GRU-based RNNs. And all of them have their own capabilities. However, all of them are supported in MIOpen, both for training and inference. Aside from convolutions and RNNs, MIOpen also supports batch normalization, reduction, CTC loss, and of course, dropout. And the details for all of these operations you can find in the MIOpen documentation. Other than basic operations, MIOpen also has an advanced feature called Kernel Fusion. So Kernel Fusion allows to merge or fuse two convolution operations together so that the kernel launch overhead as well as the off-chip memory access may be reduced. So the way operations in neural networks work is that you have operation A that is followed by operation B. So operation A would need read memory to read its input memory from the off-chip memory, which usually is expensive as compared to on-chip memory, operate on it, and then write it back. And then the operation B would come along, which would typically be another layer in the neural network. It would again read the output of the previous operation and write it back. So all of this results in redundant memory traffic, because ideally what you want is to read data once, operate on it, and then write it back. And this is what Kernel Fusion enables. It fuses different operations so that it reduces the memory traffic and forms essentially the same operation. However, we must keep in mind that not all operations are fusible. So if you have operation A and operation B, for example, in the backwards direction, then they might not even be fusible, or even if they're fusible, it might not result in performance gains that you might expect. And in fact, in some cases, it can even slow down. So all of this technicality is abstracted away by MIOpen in something called a fusion plan. A fusion plan actually holds the types of operations, their respective orders, and their various parameters. So the way it works inside MIOpen is that you create a fusion plan descriptor, which essentially encapsulates all this, the sequence of operators. Then based on that fusion plan descriptor, you create the first operator descriptor. So for example, if I wanted to fuse convolutions and activations, I'd first create a convolution operator descriptor, add it to my fusion plan, and then create the activation operator descriptor and add it again to my fusion plan. Then I would compile the fusion plan, at which point MIOpen would tell me if this operation, if this fusion combination is supported. If it is, then I would go ahead and set the auxiliary arguments, such as the input buffer, the output buffer, and any other runtime parameters that the operator has. And then I can go ahead and run the fusion plan. The important capability of this architecture is that once a fusion plan is compiled, you don't need to, if you want to rerun the same fusion plan, you don't need to recompile it with different arguments. You can just change the auxiliary arguments, such as the input and output descriptors, etc., and rerun the same fusion plan. This allows you to compile once and run many times, and thus save the initial setup time that can be costly in some cases. So the various operations that we support, fusion of our convolution, bias activation, and batch normalization. So you can have a convolution activation fusion, you can have a convolution bias activation fusion, you can have a batch normalization activation fusion, etc. For a full list of the supported operations, please refer to our documentation, which I think enumerates them in detail, as well as there's examples of how to do this in C++, and TensorFlow already implements the Kernel Fusion based on MIOpen. So in summary, MIOpen accelerates machine learning on AMD GPUs. It builds off of AMD's ROCm Stack, which provides the GPU driver and runtime, etc. It is fully integrated in with popular ML frameworks such as TensorFlow, PyTorch, Caffe2, etc. It supports a bunch of machine learning related operations, particularly convolutions, RNNs, and many other implementations. And I urge you to look at our repo to come up with, if you have any questions or if you just want to look around and gain more information. Obligatory disclaimers, etc. And that is all I had. If you have any questions, please reach out.
Traditional questions. What about successful industrial application of MIOpen? You can specify and you can tell us about.
I mean, any successful industrial application of TensorFlow on AMD GPUs would use MIOpen. So if you have a machine learning application that is vision-based and it is running on AMD GPUs, then you certainly would be directly using MIOpen. Unfortunately, the exact details of our customers are proprietary information, so that is not something that I can disclose.
Okay, understand.
Yeah, because on this level, it's not visible because this is like kind of system library supporting
Yes.
for machine application, and customer shows only like all of frameworks or even like final application and never talk what is under the hood.
Yep.
And this is the issue. But this is every customer who use AMD platform must have MIOpen. That's all.
Okay, thank you. It was a question from me, but we will wait for questions from our participants. No, we don't.
Jahandat, I have a question.
Okay.
Sure.
Yeah, about like how library is evolving. Yeah, because the question is like we have more releases, like probably like 10 releases per year for ROCm. So what's changing? If we just check in 2019, how many times it was changed and upgraded? Because I know for every platform GPU, because we're talking about like previous Vega MI100 and following product and Navi, all of those highly optimized kernels supposed to be developed like from the scratch sometimes. Like, this is only work or just something else also done usually?
So if you refer to our GitHub repo, you can see all the stuff that we are doing in terms of pull requests, right? So all the features that are going to be available or all the features that we are working on are already pull request. We are working heavily to reduce the time it takes to start up a model, like I mentioned. So you don't have to compile anything at all. That is one of our big goals. Agile development, like you mentioned, is essentially a tool that we're using to become feature complete as fast as possible, because I mean, the fact of the matter is that we have a lot of ground to catch up, right, in terms of our competition, and we want to do that as fast as possible in the best way possible. So that is how we're aiming at becoming a very good, a preferred option for running machine learning models on AMD hardware.
Two standard questions. Can you mention a key advantage of MIOpen comparing to CUDA? Yeah, or you are not direct competitors. Maybe it's in usability or compute performance.
Well, if you have an AMD GPU, could you use CUDA to run your model?
No, we're just talking about like, can you compare on functionality and just tell any advantage?
So like I mentioned, the primary purpose of MIOpen is to enable machine learning on AMD GPUs, right? And that is why AMD the responsibility of doing that falls on AMD, and that's essentially our job. We are very competitive in performance, as you usually see from corporate benchmarks that roll out with every GPU release, etc., on different machine learning models. So if you're running ResNet 50 or something on a Radeon 7 or a Vega GPU, then you would see that because of MIOpen, you can actually realize a lot of performance gain as compared to a CPU, etc. A direct comparison isn't necessarily possible because cuDNN is closed source. So even if you wanted to, you could not run it on an AMD GPU. So that is essentially our objective, is to enable a competitive implementation of convolutions and all the other primitives on AMD hardware.
Yeah, one thing is actually, even we have HIP, which actually can like using like LLVM Clang, like can generate two binaries, like one for GPU, one for AMD platform, and now one like for NVIDIA platform. This is not, we cannot directly compare, because all of our kernels, like low-level kernels, they're highly optimized on the assembly level, and on both sides. So basically, just performance comparison will be incorrect.
Correct. Right. So I guess what Timur is trying to point out is that, so in theory, you can take an MIOpen kernel and then compile it for a different GPU, right? Now, if you're using Clang, and because of the open source nature of MIOpen and ROCm in general, in theory, you can go ahead and do that, and maybe people even do that. But if you compare the performance of a ported kernel like that to a native written kernel for any architecture, it is very difficult that the performance comparison would be competitive in any way, even fair, if you might ask.
But functionally, my question is like, do we have like mirroring all of functionality of cuDNN, or just we have some missing part?
I'm not aware of any missing parts because the way we integrate is we integrate with the frameworks, right? So let's say, and our approach is that the approach of a high-level compiler. So what we want to do is to enable the frameworks to make the best use of AMD GPUs, right? Now, if they identify an operation that they could use of in performance profiling or something, and even if our competition does not have it, right? That has absolutely no bearance on our decision whether we should have it or not, right? But at least, but I believe we have a parity in functionality. So anything that you can do on an NVIDIA GPU, you can do it on AMD GPU as well.
So question, if we just have CUDA code with cuDNN calls, so like inside, what happening when we have converted to HIP and we have MIOpen calls? They're just identically replaced, or just we replaced a different way?
Generally, yes. So for all cuDNN calls, there's a corresponding MIOpen call that you can replace it with. Even it might even have, because the frameworks have to deal with both of them, right? So it essentially for every call you would need to have parity to enable the framework, right? So as far as your question is about CUDA code, so I think the tool you're referring to is Hipify. So that would take a CUDA code base and convert it into a HIP code base. And that would allow you to run it on an AMD GPU. Now, it may or may not have cuDNN calls in there. If there are cuDNN calls, then you can replace them with corresponding MIOpen calls. And I believe there is parity. And if, say, someone converts something and they don't find parity, they can always open an issue on MIOpen, and we'd be more than happy to guide them into the transformation. On the other hand, if they say have manually implemented convolutions or BLAS or maybe pooling, etc., those operations, then they can essentially replace those custom calls with MIOpen calls, and that would guarantee that they would always have the optimized kernels for those particular operations, and then not have to deal with porting and all the other stuff.
Thank you. So the question is, like, if we just work directly with framework and trying to implement all of those like framework calls, can we go directly like check for functionality, not just not just simply converting those cuDNN like calls like to like HIP level, because right now this is all the success of code hipification is like how we can support all of those CUDA application and system libraries, right? Because otherwise, like, it wouldn't work.
Actually, that is the most prevalent use case, right? So most people actually write their models in Python for TensorFlow or PyTorch, right? And all it takes is if you wanna change your underlying hardware, then the code in Python actually requires very little change. Probably just need to install different packages, and your code might even stay the same, right? Because the framework actually handles all the abstraction, and both of those frameworks have a lot of logic in them that does smart decisions around what needs to be placed where, what operations in Python map to what operations in MIOpen or cuDNN or BLAS, etc. So that is, unless you're like a power user or you have a very specific application where you're trying to eke out every millisecond of performance directly, there's very little advantage in you trying to write your own C++ model, unless you have a specific use case. For the average researcher who's doing machine learning, or even who's doing applied machine learning in the industry, you'd still at least develop your model in TensorFlow or PyTorch. And once you have it solidified, then you can convert it into either C++ or something else, and then get rid of the Python abstraction.
So basically, from our position of a vendor, we need to put on the top of MIOpen, like every framework may make it completely operational. After that, we just don't care. Like if it works, so end user on the top, they never see anything what's going on the bottom.
Essentially,
right?
Yes. But so the purpose of my presentation was to sort of crack open the hood under TensorFlow and MIOpen in particular, and show them that they have some knobs that they can further tune by and change the behavior of MIOpen, and urging them to look at the different environment variables that are available and different cache locations and all this architecture, so that if they are facing a problem, or if they see that something is not working as they expect it to be or want it to be, then they should know that which part of the stack they need to deal with, or at least ask questions.
Okay, good, thank you. So, and we are major advantage, we have open source, right? Versus QDNN, right?
Yes.
Okay, good, thank you.